In this example, we're going to look at an electron moving in an external magnetic field. So this is number 10 in your text in the end of chapter questions. And so we have an electron that is projected vertically upward with a speed of 1.7 times 10 to the 6th meters per second into a uniform magnetic field of 0.64 Tesla that is directed horizontally away from the observer. Describe the electron's path in this field. So we have an electron that is traveling vertically up the page, and then we have a constant magnetic field that is into the plane of the page. Okay, so we know from the right-hand rule that as this electron enters this magnetic field, should have drawn this here, right? As it enters the magnetic field, it's traveling with a velocity v. And from the right-hand rule, we can determine the initial direction of force. So in this situation, we have the velocity is perpendicular to the magnetic field. So point your finger in the direction of velocity, middle finger into the plane of the page. Now we have to take into account that this is an electron which has a negative charge. So if it is negative, then our resultant force is going to be opposite what it would for a positive charge. So it is going to experience a force to the right, right? And as it continues on its path, its original vertical trajectory is going to be curved, okay? So what we've seen is that the electron will continue along this curved path it will have a centripetal acceleration, right? So from Newton's second law, you should remember that the net force acting on an object is equal to mass times the acceleration, okay? In this instance, we are going to ignore gravity because we are dealing with an electron whose mass is very, very, very small. And so the force due to gravitational acceleration is going to be very small compared to the force from the magnetic field on the charged particle. So our net force is going to be our force due to the external magnetic field. So we can set these equal, and again we're using the maximum version of our equation because our velocity and magnetic field are perpendicular to one another. So this is going to be equal to QVB. Okay, so if you remember from first semester biophysics, which you probably don't, centripetal acceleration is equal to the speed squared over the radius of the path. Okay, so we can substitute n for a, and so this becomes mv squared over r equals qvb. And so to describe the path of the electron, the most descriptive property is the radius of its path. So we can determine that, rearrange, so we get that R is equal to mv over qb. So we have, now at this point, we just substitute in, and the mass of an electron, I'll write up here for a constant, is going to be equal to 9.11 times 10 to the negative 31 kilograms. And our charge, or I should say the absolute value of our charge, because we are doing a magnitude here, is going to be equal to 1.6 times 10 to the negative 19 coulombs. Okay, so we're just substituting in and our velocity is 1.70 times 10 to the 6th meters per second over our charge times the strength of our magnetic field, which is 0.640 Tesla. Okay. And we get a radius of 1.5 times 10 to the negative 5 meters. Okay. So the path of this electron is going to curve to the left, and depending on the area of the magnetic field, more than likely this, if it is entering here, takes a curved path, it's going to make a semicircle with a radius of curvature of 1.5 times 10 to the negative 5 meters.